Lab 6. Amanda Acosta, Alyssa Rodriguez, Alyssa Olguin, Montserrat Nunez.
Capacitors are electrical components that store energy in the form of an electric field and release it when needed. They play an important role in modern electronics, where they are used in batteries, signal filtering, and correcting electrical signals in the circuits. One common way capacitors operate is through repeated charging and discharging cycles. In a simple resistor capacitor RC circuit, the charging and discharging process occurs rapidly at first and then gradually slows until it stabilizes. A key quantity that describes this behavior is the time constant, which is like stands for T, which is equal to the product of the resistance and capacitance in the circuit T equals RC. The time constant represents the time required for a capacitor to charge to about 63% of its maximum voltage. In this experiment, an RC circuit was constructed using a signal generator, a resistor, and a capacitor to observe the charging and discharging process. By measuring the voltage across the capacitor over time, the experimental time constant was determined and used to calculate the capacitance. These values were then compared to the theoretical capacitance to analyze percent error and understand possible sources of experimental uncertainty.
Capstone software. The software was used to control the signals and record numerical data. It allowed us to see the voltage time graphs. It was also used to obtain our time constant. The voltage and current sensor was used to measure the voltage for this experiment. With this, we were able to identify when the capacitor reached 63% of maximum voltage. Capstone software. The software was used to control the signals and record numerical data. It allowed us to see the voltage time graphs. It was also used to obtain our time constant. The voltage and current sensor was used to measure the voltage for this experiment. With this, we were able to identify when the capacitor reached 63% of maximum voltage.
In this experiment, we studied how a capacitor charges and discharges in an RC circuit. We set up a square wave signal and recorded the voltage across the capacitor over time. We measured the time it took to reach 63% of the maximum voltage to find the time constant and calculate the capacitance. Then we repeated the process with the capacitors in parallel and compared our experiment values to the theoretical ones. Finally, we analyzed the percent error and possible sources of error in the setup.
So basically, all of what you have is correct. You only have like your graph is shifted like to the negative 2 volts for the resistance and also for the time. So you can see that it is actually like a difference of 0.004 seconds. So and they also have like an internal resistance. So it might not be as high as 1 ohm, but they have some resistance. Okay. Connecting the two capacitors together in parallel. So basically, when you have two capacitors together, it is going to be in parallel. You're just going to be adding the capacitance of both of them. So for step 2, the theoretical capacitance is just going to be 330 plus 100, which is going to be 140 microfarads.
You mean 130?
You're 430?
430, yeah.
We all got the numbers wrong.
And in microfarads, it will be times 10 to the negative 6. And there will be in farads. And we're just gonna do the same. We're gonna run it again. I mean, now you can see that actually the time interval is larger, and that is because the tau it is proportional. So because we're starting to the negative 2.06. So we're just gonna start at 0.5 again. So the closest value to 1.09 is 1.1, and it will be 0.517 seconds. Adding it to 2.06, which is going to be the resultant voltage, like the in the graph.
Table 1, experimental values for one capacitor. This table includes the experimental values found for one capacitor. T1 had a value of 0.5 seconds, and T2, when the voltage was 63%, was 0.504 seconds. Tau, or T2 minus T1, was found to be 0.004. Our experimental capacitance, CE, was found by dividing tau by 33, giving us 0.00012. Our theoretical capacitance was found by multiplying 33 by 100 times 10 to the negative 6th, giving us a value of 0.0033. Finally, we had a percent error of 96%. Table 2, experimental values for two capacitors in parallel. When two capacitors were in parallel, we found that our time T1 when V equaled negative 2.06 was 0.5 seconds. Our T2 when voltage was 63% was 0.517 seconds. Tau, T2 minus T1 was 0.017. Our experimental capacitance was found by dividing tau by 33, giving us a value of 5.15 times 10 to the negative 4. Our theoretical capacitance was 0.014, giving us a percent error of 3000%. Conclusion. After conducting this experiment, our group was able to observe and calculate the time constant in an RC circuit. In this lab, we observed and documented the time constant in circuits that had either one capacitor or two capacitors in parallel. We found that even though our values in each table were fairly similar, when we calculated for percent error and the time constant, we had high percent error values that were not close to each other or to their respective theoretical values. Our group believes that the high percent error values were probably due to the high number of wires that were connected for each circuit. Such errors could potentially decrease if the amount of wires was lowered, since each wire was affecting the experiment setup and overall resistance and capacitance. Additionally, if our equipment was better quality, perhaps each wire's interference would not be so detrimental to the data. When conducting our experiment, our group found that our time constants were somewhat similar, but for the context of this lab, they were very different. Our group believes that the time constant should be slightly different because we were changing the setup of the circuit. However, because the setups were not completely different, the time constants should still be close in value. Our percent errors were similar in the sense that they were both significantly high. However, they were not close in value, 96% and 3000%. Our group believes that percent error should be different between the two circuits because there are new variables that can cause error. However, because the change in setup was not drastic, The percent errors should not significantly differ from one another. After considering the capacitance value as the one in the circuit, the errors were different from the ones with the capacitances, but still had high percent error. Our group believes that the percent error should once again be somewhat different due to the difference in the setup and addition or removal of materials. The addition of materials could contribute to increased percent error because, as we previously observed, the materials each have their own capacitances and further complicate the data because they are not the most efficient equipment, thus increasing the chance of error. Overall, our group was able to learn about time constants and their importance in RC circuits. Even though our experiment did have high percent error values, primarily due to equipment, we were able to learn about these important principles. Credits: Introduction, Video Recording, Amanda Acosta. Materials, Montserrat Nunez. Procedure, Alyssa Olguin. Data, Alyssa Rodriguez. Conclusion, Alyssa Rodriguez. Credits,